Welcome to Orbit Observer. Tonight, I want to take you somewhere that almost nobody thinks to look. Not out past the rings of Saturn, not to the pale blue dot of Neptune, not to any of the famous places you already have a picture of in your mind. No. Tonight, we are going somewhere plain. Somewhere that most people, if they think of it at all, imagine as a grey and lifeless nothing. A lump of rock drifting in the emptiest, least glamorous corner of the whole solar system. And I want to show you that this plain and forgotten place is hiding something extraordinary. Something that, by every rule we thought we understood, should not still be there. And yet, it is. It is there right now, and part of it may still be glowing. So settle in. Let your shoulders drop. There is nowhere to be, and nothing to solve. Let me be the one to stay awake and keep watch while you drift down slowly into this story. Picture a crater. It sits on the surface of a small, dark world, and it is wide, about 92 kilometers across, which is to say, if you stood at one rim, you would not be able to see the other side. It would curve away below the horizon. This crater has a name. It is called Occator, and the world it sits on is darker than you can easily imagine. Not dark like a moonless night, dark like fresh asphalt, like a road surface, still wet and black under a street lamp. This little world reflects only about 9% of the light that falls on it. 9%. Think of a piece of coal, or the charred remains of a campfire log, that dull, sooty grey that seems to swallow the light rather than throw it back. That is the colour of nearly everything here. It is one of the darkest surfaces we have ever mapped anywhere in the solar system. And in the middle of that darkness, inside Occator crater, there is a spot of the most brilliant, startling white. Imagine that for a moment. Imagine standing on this cold and ancient dark plain, everything around you the colour of soot and shadow, and then, in the floor of this great bowl of a crater, a patch of something so bright, so reflective, that in the first images we ever took of it, it looked less like a mineral deposit and more like a light, like a torch someone had left burning down there. When the spacecraft that found it first sent home those pictures, the spot was so brilliant against the surrounding dark that people genuinely struggled to believe it was real. It looked like it was shining with its own inner glow. That bright patch has a name too, and it is a beautiful one. It is called Cerealia Facula. And that word, facula, comes from Latin. It means, quite literally, little torch. A little torch, burning inside a crater on the darkest world we have ever seen, and a short way to the east of it there is a whole scattered cluster of smaller bright patches, fainter cousins to the first, and those are called the Vinalia Faculae, the little torches. That is what the people who first mapped them chose to call these strange glowing marks, because that is exactly what they look like. Points of white fire on a field of ash. Now here is where the story begins to turn, and I want you to stay with me, softly as it does. Because the obvious question, the one everyone asked, was simply, what is it? What is this bright material? And I could tell you the plain answer. The one you might have heard before if you have ever caught the tail end of a documentary about this place. The bright stuff is salt. That is the flat headline. It is salt. But that answer, on its own, is where most tellings stop. And it is a shame, because stopping there is like walking up to the door of the most interesting room in the house and then turning around and leaving. Because it is not just that it is salt. It is what kind of salt. And it is the fact that this particular salt, chemically, physically, by everything we understand about how it behaves, should not still be there at all. Let me explain what I mean slowly, because this is the heart of the whole thing. This is the mystery that everything else tonight will circle around. Among the salts that were found glowing in Occator crater, there is one in particular that matters more than all the rest. Its name is Hydrohalite. And I know that is a mouthful of a word, so let me unpack it gently, the way you might unfold a piece of paper that has been folded up tight. Ordinary table salt, the kind in the shaker on your kitchen table, is a compound of sodium and chlorine. Sodium chloride. Hydrohalite is that same salt, sodium chloride, but with water molecules built directly into its crystal structure. It is, if you like, a wet salt. A salt that has locked little pieces of water inside itself in a very specific and delicate arrangement. Scientists write it as sodium chloride dihydrate, which just means 2 water molecules bound up in the crystal for each unit of salt. Think of it like a sugar cube that has soaked up moisture and gone soft and clumpy, except here the water is not just clinging to the outside, it is woven into the very lattice of the crystal itself, part of its structure. And here is the thing about hydrohalite. Here is the thing that makes it, to my mind, one of the most quietly astonishing details in all of planetary science. Out on the surface of this small, cold, airless world, hydrohalite is not stable. It cannot last. The conditions on the surface, the vacuum, the way the sun works on it, the utter dryness of open space, they pull those bound water molecules right out of the crystal. The hydrohalite dehydrates. It dries out, and when it dries out, it stops being hydrohalite and simply becomes ordinary halite, plain dry salt, the water gone. And this does not take a long time. This is the part I need you to hold on to as you drift. This drying out, this dehydration, happens on a time scale of years. Years to at most a few centuries. In the life of a world that is billions of years old, that is nothing. That is the blink of an eye. That is less than nothing. If this were a single day in the life of that world, we would be talking about a fraction of a single second. So sit with the strangeness of that. When the spacecraft looked down into Occator crater and detected hydrohalite, and this, by the way, was the very first time we had ever found this particular wet salt anywhere off the surface of the Earth, the first detection in the entire solar system beyond our own planet. When it found that hydrohalite sitting there in Cerealia Facula, it was finding something that should have already fallen apart. Something that, if it had been sitting there undisturbed for millions of years, for even thousands of years, would long ago have dried out into ordinary salt and lost its telltale signature. But it had not. It was still wet. It was still hydrohalite. And there is only one way to make sense of that. Only one explanation that fits. If the hydrohalite is still there, still holding its water, still fresh, then it cannot be old. It has to have arrived at the surface recently. Geologically speaking, it has to have arrived almost yesterday. And more than that, because this wet salt keeps drying out and would need to be constantly replenished to stay visible, it means whatever process put it there may still be going on. Right now. Even now, as you lie there listening. Do you see what that means? Do you feel the size of it? Something is delivering fresh, wet, briny salt to the surface of this crater in the present day. Not billions of years ago, in some dead and finished past. Now, and to deliver briny salt to the surface, you need brine. You need liquid, salty water. Which means that somewhere below the floor of Occator crater, below that dark and frozen surface, there is liquid water. There is a sea, or the remnant of one, and it is still, in some quiet and buried way, alive, That is the master mystery of tonight. That bright torch of salt is not just pretty. It is a signal. It is a chemical clock, and the clock is still running. And the fact that we can read it, the fact that it has not yet wound down, is proof that this supposedly dead little world has liquid water inside it in the present tense. Now, I said this is a mystery, and I want to be honest with you about how much of it we truly know and how much we are still working out, because that honesty is part of what makes it worth staying with. We know what the salt is, that is measured, that is real. We know how fast hydrohalite dehydrates, that is chemistry, tested and understood. But there is so much we still cannot say for certain. Nobody knows exactly how the brine finds its way up through kilometers of rock and ice to reach the surface. Nobody knows precisely how much liquid remains down there, or how long it will last, or whether the plumbing that feeds these bright torches will keep working for another 1,000 years, or shut down tomorrow. Nobody can tell you, with full confidence, whether the spots are still growing at this very moment, brightening grain by grain, or whether we caught them in their final act. There is no spacecraft there now to watch. We are left reading a clock we cannot fully see, on a world we visited once and then left behind. That is the shape of it. Something that should not still exist. That does. A process that should have stopped long ago, that seems not to have. And beneath it all, a body of liquid water in the last place anyone thought to look for one. So let me tell you where exactly this is. Let me widen the view and take you up and out so you can see this little world in its place and understand just how unlikely and how overlooked it is. The world I have been describing is called Ceres. And Ceres lives in a place you have almost certainly heard of, even if you have never given it a second thought. The asteroid belt. That great scattered ring of rocky rubble that lies between the orbit of Mars and the orbit of Jupiter. When people picture the asteroid belt, they usually imagine something out of a film. A dense and dangerous swarm of tumbling boulders, packed so close you would have to weave between them. The truth is far emptier and far lonelier than that. The asteroid belt is vast, and its pieces are so spread out that if you were standing on one of them, you would likely see nothing but stars in every direction. It is a thin, quiet scattering of debris, left over from the birth of the solar system, drifting in the cold sunlight halfway between the red planet and the giant one. And Ceres is the largest thing out there, by a wide margin. It is the biggest single object in the entire main asteroid belt, so large, in fact, that it holds something like 1/4 to 1/3 of the total mass of the whole belt all by itself. All those thousands upon thousands of other asteroids, all the rocks and boulders put together, and this one world accounts for a full quarter or more of everything. It is, in its neighborhood, a giant. And yet, by the standards of planets and moons, it is small. Its mean diameter is about 940 kilometers, a little under 600 miles. To give you a sense of that, you could fit something like 13 Ceres-sized worlds inside our own moon. It is a modest thing, as worlds go. A small dark sphere in an empty place. But here is the detail that changes everything, the detail that lifts Ceres up out of the category of ordinary rock and into something far more remarkable. Ceres is not classified as an asteroid anymore. Ceres is a dwarf planet. It is the only dwarf planet in the entire inner solar system. Every other object we recognize as a dwarf planet, every single one, lies far out beyond the orbit of Neptune, in the cold and distant reaches at the very edge of the Sun's family, out where Pluto drifts through the long dark. Ceres is the only one on our side of Neptune, the only one anywhere close to the warmth of the sun. And now let me give you the fact that reframes this whole plain grey lump, the fact that most people have simply never been told. We have come to know over the last decade or so that there are certain worlds in the solar system that hold oceans of liquid water hidden beneath their frozen surfaces. Ocean worlds, we call them. You may have heard some of their names. Europa, one of the moons of Jupiter, with a deep sea sloshing beneath its cracked ice shell. Enceladus, a small moon of Saturn that sprays plumes of salty water out into space from a hidden ocean below. These are the celebrated ones, the darlings of the search for life beyond Earth. And they are wonderful. But they are far, far away, out among the giant planets. Hundreds of millions of kilometers past Ceres, and here is the quiet, astonishing truth. Ceres, that grey lump in the junkyard that overlooked nothing between Mars and Jupiter, is also an ocean world, and because it sits so much closer to us than Europa or Enceladus, it is, in fact, the closest ocean world to the Sun. The nearest place to home where liquid water hides beneath a frozen crust. Not out past Pluto, not out among the great ringed giants. Right here, in the least glamorous, most ignored corner of the solar system, in the dusty rubble field, everybody skips over on their way to somewhere more exciting. An ocean world, hiding in plain sight, the whole time. And almost nobody noticed. That is what I want to give you tonight. Not the tired old story you may have half heard, the one that goes mysterious bright spots, baffled the scientists, and then, oh, it turned out to be salt. The end. That version robs you of everything good. The real story is so much richer and so much stranger. The real story is that we found a dying sea, caught in the slow act of freezing, in the last place anyone thought to look, and that it left us a signature written in salt and light to prove that part of it is still alive. Before we go deeper, and we will go deep, I want to do one small thing, the way I always like to. I would love to know where in the world you are listening from tonight. It is a strange and lovely thing to think that this same quiet story is being carried out to people lying in the dark, in so many different places, under so many different roofs, in so many different time zones, some of you just getting into bed, some of you awake in the small hours. If you feel like it, leave a note in the comments and tell me where you are. I read them, and there is something comforting in seeing all those distant lights gather around one small story. And if you are new here, if you have just wandered in tonight and found this place, you are very welcome. Consider subscribing so that whenever you need a slow and careful voice to walk you down into sleep, you can find your way back. There is no rush. The story will wait for you. Now let me set the pace for the rest of our night together, so you know what to expect and can let go completely. We are not going to hurry. We are going to descend into this mystery the way you might walk down into a deep cellar with a single lamp, one careful step at a time, letting your eyes adjust to each new level of the dark before moving on to the next. We are going to look at what this world is and how we came to find it and how a single patient spacecraft crept up on it and orbited it and mapped every bright and dark inch of it. We are going to understand what that salt truly is, all of it, not just the headline. We are going to find a mountain, a lone mountain, 4 kilometers tall, that has no business standing where it stands. And we are going to learn why it is alone. We are going to find the fingerprints of a space telescope that caught this so-called asteroid doing something asteroids are not supposed to do, long before any spacecraft ever arrived. And we are going to find, woven through all of it, the ingredients of a chemistry so rich and so suggestive that it makes you look at this small, dark world with a kind of wonder. You do not need to remember any of it. You do not need to follow every thread or hold every number in your mind. Let the details wash over you like water. If you fall asleep before we reach the bottom, that is not a failure. That is exactly what this is for. That is the whole point of me being here. I will keep going quietly, whether you are still with me or not, laying down the story piece by piece, and you can simply let the sound of it carry you under. There is no answer you need to stay awake for. In fact, part of the beauty of this particular tale is that there may be no neat and tidy ending at all. The mystery of Ceres is a real one, an open one, and some of it we may never fully solve. And that is all right. That is the kind of mystery that is soothing to wander into, rather than one that keeps you tense. Nobody is going to jump out. Nothing is going to startle you. It is just an old, cold, quiet world and a slow story about the water it hides. So let me take you back, for a moment, to how any of this was even possible. Because a world as dark and small and far away as Ceres does not give up its secrets easily. For most of the time that humans have known Ceres existed, and we have known of it for well over 2 centuries now, it was little more than a faint point of light in a telescope, a dim speck that moved slowly against the fixed stars from one night to the next. A dot. Nothing more. You could not see its dark surface, or its bright torches, or its craters, or its lonely mountain. You could not even be sure what it was made of. For generation after generation, Ceres was just a moving point in the eyepiece, a number in a catalogue, a faint traveller whose true nature was completely hidden from us. To turn that faint speck into the world I have been describing to you, to see the darkness of its surface and the brilliant white of its salt, to measure the very chemistry of Cerealia Facula, to weigh the water inside it and read the clock ticking in its crystals, someone had to go there. Someone had to send a machine across the vast emptiness of that inner solar system, out past the orbit of Mars, into the belt itself, and bring it to a gentle halt in orbit around this small dark sphere, and let it look and keep looking, month after month, spiraling closer and closer until it was skimming just above the surface. And that is exactly what we did. There was a spacecraft. It had a name, and a long and patient journey, and an ending that is, in its own quiet way, as haunting as anything else in this story. But that is where we will pick up the thread. For now, just hold the picture in your mind as you drift. A dark world, the colour of soot, alone in the empty belt between Mars and Jupiter. And on that dark world, inside a great wide crater called Occator, a patch of salt so bright it looks like a little torch left burning in the black. A torch made of a wet salt that should have dried out and vanished long ago, but has not, because something beneath the ground keeps feeding it, keeps the water flowing, keeps the strange clock ticking. The closest ocean world to the sun, hidden where nobody thought to look. A sea that is mostly frozen now, but not entirely. Not yet. Not all the way. Let that image hold you. The little torch, burning in the dark. And let me carry the story forward from here, softly, while you rest. Now, before we go any further, before the spacecraft and its long patient fall toward the surface, before the ice volcano standing alone and the water breathing off a rock that had no business breathing at all. Let me ask you something small and simple, the way I always do at the start of these slow journeys. Wherever you are right now, whatever dark and quiet corner of the world is holding you as you settle in to rest, I would like to know where that is. Somewhere out there, in a bed in a city, in a house at the edge of a field, in a room where the only light is the glow of the screen going dim. You are listening. Leave a word in the comments, if you feel like it, telling me where in the world you are drifting off tonight. And if you are new here, if you have only just wandered in out of the dark, you might press subscribe so the next slow story finds its way to you when you need it. That is all. Now let the picture come back. Because here is the thing that makes this world different from every grey lump and tumbling stone in that belt, the thing that turns a dead cinder into a mystery worth spending a whole quiet night inside. The salt should not be there, not the way it is, not still. When the machine we sent looked closely at the brightest heart of that crater, at the deposit called Cerealia Facula, the little torch itself, it did not simply find salt in the general, ordinary sense. It found a very particular kind. Sodium carbonate. Yes, one of the largest gatherings of carbonate salt anywhere off the face of the earth. But tangled in with it, at the very brightest centre, the instruments picked out something stranger and far more fragile. Hydrohalite, sodium chloride dihydrate, if you want the full and formal name of it, common table salt, the salt of every ocean and every kitchen, but with water molecules locked into the very structure of its crystals, 2 of them for every unit of salt, held there like breath held inside glass. A wet salt. A salt still carrying its water. And this is the part to hold on to as you sink, because everything else in the story hangs from it. Hydrohalite is not a patient mineral. Out in the open, in the cold and the vacuum and the slow bath of sunlight that falls on the surface of Ceres, it does not last. It gives up its water. It dries out and falls apart and reverts to plain, ordinary, unremarkable salt. And it does this not over the long geological ages that planetary scientists usually count in, not over billions of years, not even over millions, but over years. Years to centuries. A geological eyeblink. A single held breath in the life of a world. So sit with what that means. The instruments found this fragile, water-bearing salt sitting exposed at the brightest point of Occator crater. Gleaming, intact, undried, and a salt that falls apart in years to centuries cannot have been sitting there for the 20 million years since the crater was carved. It cannot have been sitting there for 1 million years, or even, comfortably, for 100,000. It is a clock. It is a clock that has almost run down and is somehow still ticking. And the only way it can still be ticking is if something keeps winding it, if fresh briny water keeps rising up from somewhere beneath the crust and reaching the surface and leaving new salt behind, again and again, in a timescale so recent it may as well be yesterday. It may, in fact, be happening now. As you lie there, as the world turns under you. That is the enigma at the centre of this whole slow descent, and I want you to feel how much larger it is than the tired old story. For years the fashion was to talk about the bright spots as a puzzle of appearance. What are those glowing lights? Why do they shine so? What could make them gleam like that on a world so dark? And that puzzle, in its way, was solved. The spots are salt. But the real mystery, the one the field so often steps right past, is not what the spots are made of. It is why they are still here at all. Nobody built them to last. Nobody expects a wet salt to survive on an exposed surface for more than a geological instant. Nobody can point to a warm, obvious, still-running engine on a body this small and this cold and this far from the sun and say, there, that is what keeps feeding it. And yet the salt is here, bright and undried, ticking away. Nobody knows with certainty how deep the water goes. Nobody knows how long it will keep rising. Nobody can say for sure whether the little torch is still growing, brighter tonight than it was the day we last looked, because the one machine that could have told us fell silent before it could watch long enough. 3 unknowns, stacked one upon the other, and beneath all 3 a single strange and quiet fact refusing to go away. Something down there is still liquid. Something is still moving in the dark. And now let the frame pull back, slowly, the way a camera lifts away from a single lit window until it can see the whole dark city around it. Because this is not some distant exotic outpost at the far frozen edge of everything. When people speak of ocean worlds, of hidden seas beneath crusts of ice, they almost always point outward, far out, past Jupiter, past Saturn, to the famous frozen moons where such things are supposed to live. But this world, this small dark sphere with its ticking salt, is not out there at all. It is close. It is the closest ocean world to the sun that we know of, the nearest hidden sea to the warmth and the light, and it has been sitting there in plain view the entire time, in the one part of the solar system we long dismissed as a junkyard. It rides in the belt between Mars and Jupiter, that wide scattered ring of rubble and stone we learn to think of as leftovers, as debris, as the broken pieces of a planet that never quite came together. And of all the countless bodies tumbling through that belt, this one is the largest. Large enough, round enough, held firmly enough by its own gravity that we do not call it an asteroid at all. We call it a dwarf planet. And here is the quiet marvel folded into that name. It is the only dwarf planet in the entire inner solar system. Every other world we have granted that title lies out beyond Neptune, out in the deep cold dark at the far rim of everything. This one alone sits on our side of that great divide, inside the orbit of Neptune, inside the belt, close enough to feel like a neighbour. A hidden ocean world, dark as soot, wearing a torch of ticking salt, parked in the last place anyone thought to look for a sea. So that is where we stand, at the mouth of the long descent. There is a world. There is a great wide crater on it called Occator. There is a bright, fragile salt at the crater's heart that should have vanished ages ago and has not, because a mostly frozen ocean beneath the ground is, it seems, not entirely finished. And there was a machine once that carried our eyes all the way out there and let us see it, and to that machine and its patient journey and its long, slow fall through orbit after orbit toward the surface. We will come very soon. For now, breathe slowly. Hold the little torch in your mind, burning quietly in all that dark. And let me keep walking you inward, gently, toward the thing at the bottom of it all. The man who found it was not looking for it. That is perhaps the most honest way to begin. On the first night of the year 1801, a Sicilian astronomer named Giuseppe Piazzi sat at his telescope in the city of Palermo and moved it slowly along a familiar stretch of sky, cataloguing stars, doing the patient, methodical work that most of astronomy is, most of the time, not discovery, not drama, but the slow accumulation of positions and measurements, the kind of work that fills notebooks rather than history books. And on that particular night, he noticed something that was not quite where it had been the night before. Not a star, then. Stars do not move. Not on the time scale of a night. not in any way an eye can detect. This was something else, something that drifted, something in motion against the fixed background of everything, the way a boat moves against the shore, the way a candle carried across a room moves against the still dark beyond the window. He noted it. He returned to it, and over several nights he confirmed that it was real, that it moved with purpose and regularity, that it traced a path that placed it somewhere between the orbits of Mars and Jupiter, in the wide emptiness that astronomers of that era had long suspected held something but had never quite found. He named it Ceres Ferdinandia, partly in honour of the Roman goddess of the grain harvest, and partly, as was the custom and the politics of the time, in honour of Ferdinand, the King of Sicily. The royal half of the name did not survive. The goddess did. And so the world we are walking toward tonight has carried a goddess's name for more than 2 centuries. And that is fitting in ways that go beyond mere tradition, because Ceres the goddess was the keeper of living things, of wheat and seed and the earth's capacity to feed. And Ceres the world, as we now know, keeps something of its own, holds it deep, under pressure, under cold, under dark, something that living things, wherever they have ever arisen, have always needed. But we are not there yet. We are still in 1801, still in Palermo, still watching a point of light drift slowly against the stars. Piazzi's discovery was announced to the scientific world, and the scientific world had thoughts about what this thing was. At the time, astronomers had been expecting to find something between Mars and Jupiter, an arithmetic argument, the Titius-Bode law, a pattern of planetary spacings that seemed to predict a body there, in that gap, as though the solar system had left a place at the table and no one had shown up to fill it. Piazzi's wandering light seemed, at first, to fill that seat. It was assigned the status of a planet, the 8th planet, and for a few years that is what it was, a planet, small but a planet, deserving a symbol and a place in the ordered family of worlds. Then the complications arrived. Other objects turned up in the same region, not one but many. A second body was found, and a third, and a fourth, and they kept coming, small worlds and smaller worlds and rocks with no names, tumbling through the same broad zone between Mars and Jupiter. And it became increasingly clear that what Piazzi had found was not a lone planet sitting neatly in its lane, but something more like the largest resident of a crowded neighbourhood, the biggest house on a block, where every house is small and the street runs for hundreds of millions of kilometres. Gradually, Ceres was reclassified. Not a planet after all, they decided. An asteroid. The first and largest of the asteroids, certainly, but an asteroid nonetheless, a rock among rocks, a rubble dweller in the belt that eventually took the name its residents suggested, the asteroid belt. And so Ceres disappeared from the table of planets and spent roughly a century and a half in the company of minor bodies, a category that suggests something like geological modesty, something unimportant, something not worth lingering over. Textbooks mentioned it as a footnote. Students learned it, if they learned it at all, as the biggest lump in the belt. It was present in the scientific record, but it was not, precisely, interesting. Not to the culture, not to the popular imagination, not to the people who write the kind of books that end up on shelves in houses where children grow up wondering what is out there. Then 2006 arrived, and everything got reshuffled again. The International Astronomical Union, meeting in Prague, undertook the uncomfortable task of defining what a planet actually is. The solar system had by then become complicated in ways that demanded clarity. New objects had been found out beyond Neptune, Pluto's companions, bodies in the Kuiper belt, some of them very large, some of them arguably large enough to sit at the same table where Pluto sat. If Pluto was a planet, the argument ran, then some of these new discoveries might also be planets, and the number of planets in the solar system could grow uncomfortably quickly. So the OW decided to draw a line. They wrote a definition, and under that definition, a planet must do three things. It must orbit the Sun, it must have enough mass for its own gravity to pull it into a roughly spherical shape, and it must have, in the language of the resolution, cleared the neighbourhood around its orbit. That third criterion was the one with weight. Pluto failed it, it shares its orbit with many other Kuiper belt objects, and so Pluto was reclassified, demoted in the popular imagination, mourned by some and accepted by others, and debated to this day in corners of the internet where such things are debated with great passion. But Pluto's demotion is the story that everyone remembers. The quieter part of that same 2006 decision is less often told. Because the OW simultaneously created a new category, the dwarf planet, for bodies that met the first two criteria but not the third, they orbit the Sun, they are round, but they share their orbital neighbourhood with others. And into that category, that same year, on that same day, two bodies were admitted together. One was Pluto, falling. The other was Ceres, rising. After more than a century and a half as an asteroid, Ceres was elevated, reclassified, promoted to a new status. Not a planet, not merely an asteroid, a dwarf planet. The only dwarf planet sitting on the inner side of Neptune's orbit, the only one close enough to be called, in any meaningful sense of the word, a neighbour, which means Ceres has a stranger and more turbulent biography than almost any other object in the solar system. Found as a star that was not a star, promoted to planet, demoted to asteroid, elevated to dwarf planet, all within the span of human civilization's increasingly precise instruments and increasingly argued categories. It has been reclassified more times than any other world we know. It is, in a sense, an object that keeps refusing to fit the box we build for it, and that refusal, it turns out, goes much deeper than questions of orbital mechanics and nomenclature. The name, though, has stayed constant through all of it. Ceres, the harvest goddess, the keeper of grain, of growth, of the fertile earth. In her mythology, she was the mother of Proserpina, the figure who was taken down into the underworld and for whom Ceres grieved so deeply that the world above grew cold and barren until her daughter was returned. That story is the origin of the seasons, in the old telling, summer and abundance when Proserpina is home, winter and cold when she is gone. And there is something quietly beautiful in the fact that the world bearing her name holds, beneath its surface, a kind of frozen sea, a body of water interrupted, a warmth withdrawn, a liquid future held in suspension. The parallel is loose, and it would be wrong to press it too hard, but it breathes there if you let it. There is one other small etymology worth noting here. In the quiet. The word cereal, the grain, the breakfast bowl, the field of wheat moving in the wind, shares its root with Ceres. The goddess of the harvest gave her name both to a dwarf planet in the asteroid belt and to every box of cornflakes ever printed. It is the kind of small, specific connection that is easy to forget and somehow impossible to forget once you know it. But let us come to the body itself, the physical fact of this world. Because understanding what Ceres actually is, in terms of size and substance, is essential to understanding why what is inside it is so surprising. Ceres has a mean diameter of roughly 940 kilometers, that is approximately 590 miles. To make that number feel like something, the contiguous United States, from the Atlantic coast to the Pacific, spans about 4,500 kilometers. Ceres, placed on that map, would not stretch from New York to Boston. It would sit inside Texas with room to spare. It is a small world, genuinely, unambiguously small. And yet its gravity is sufficient to have pulled it into a roughly spherical shape, which is why it qualifies as a dwarf planet at all. Small enough to carry easily in the mind, large enough to be round. If you could stack 13 bodies of Ceres's mass and pack them together, you would still fall a little short of the Moon's total mass. In the company of the solar system's true planets, Ceres is a pebble. Its bulk density is approximately 2.16 grams per cubic centimeter. That number matters because it tells you, quietly but precisely, what a world is made of. Rock, for comparison, typically runs between 2.5 and 3.5 grams per cubic centimeter. Pure water ice sits around 0.9. Ceres at 2.16 is measurably lighter than solid rock. And the reason models and measurements agree on is that it is not all rock. There is a substantial fraction of ice and other volatile material mixed through its substance, water locked in various forms, threaded through the interior in a proportion that planetary scientists estimate at somewhere around a quarter of Ceres's total mass. Roughly 25% water, by mass, in a world that has been sitting in the asteroid belt for 4.5 billion years. And that fraction, when you translate it into actual volume and compare it to something familiar, produces a number that is genuinely arresting. The fresh water in all of Earth's rivers, all of Earth's lakes, every river on every continent. Every lake from the Great Lakes to Lake Baikal, to every high alpine tarn and every slow lowland basin, adds up to a quantity that Ceres likely exceeds, locked in its ice and its brine, held under its dark and unremarkable-looking surface. Not the oceans. Earth's oceans dwarf everything, and this comparison is not about salt water, but the fresh water, the rivers and lakes. The accessible blue of living geography, all of it, on one world. All of it, on a world that looks, from any reasonable orbital distance, like a grey and largely featureless ball, 940 kilometers across, sitting quietly between Mars and Jupiter, and doing, from the outside, very little that suggests abundance. This is the thing that the solar system keeps doing to us. It keeps hiding its remarkable things inside its ordinary packaging. It places an ocean world in a junkyard. It fills a dull grey sphere with more fresh water than the surface of the only living planet we have ever known. And it does it so subtly, at such remove, that for most of human history we simply did not see it. We needed a machine to go and look. The machine had a name, and the name was Dawn. NASA's Dawn spacecraft was conceived as a mission to the asteroid belt, to the inner solar system's most populous and least studied neighborhood. Its original targets were two of the belt's most scientifically interesting large bodies, Vesta, a protoplanet, an ancient rocky world that had differentiated and partially melted and been battered by collisions across billions of years, and Ceres, the dwarf planet, the round one, the one with the anomalously low density and the hints of something volatile within. The ambition of the mission was unusual. Most deep space probes are designed to visit one destination. The geometry of orbital mechanics is unforgiving. The energy required to enter orbit around one body and then leave and travel to another is enormous, typically prohibitive. You do not, in the ordinary physics of rocket propulsion, get 2 for 1. You go somewhere, you study it, you move on. The fuel costs are too great. Dawn found a way around this. Not by bending physics, but by playing a different game within it. Instead of chemical rockets, which burn intensely for short periods and then go cold, Dawn used an ion propulsion system, a technology that works by taking atoms of xenon gas, the same dense, heavy noble gas that fills certain kinds of theatrical and photographic lighting, and accelerating those atoms electrically until they stream out the back of the spacecraft as a jet of charged particles. The thrust produced is almost comically small by the standards of conventional rocketry. The force of a Dawn engine running at full power is approximately equivalent to the weight of a single sheet of paper resting on your open hand. You would not feel it if it were pressing against your skin. But thrust applied continuously for weeks, for months, for years, that changes the arithmetic entirely. A gentle, unrelenting push accumulates. It adds up, day after day, into velocity, into trajectory, into the ability to decelerate into orbit around one body, spend more than a year studying it, and then accelerate again toward a second body, many hundreds of millions of kilometers away. Dawn departed for Vesta, reached orbit in 2011, studied the ancient protoplanet through 2012, and then did something no spacecraft had ever done before. It fired its ion engines and left one extraterrestrial body's orbit to go enter another's. It took what had been achieved at Vesta, the data, the portraits, the measurements, and it turned its cameras toward Ceres, and it began the long, slow, xenon-fueled fall toward the grey dwarf planet in the dark. It arrived at Ceres in March 2015. That month, that moment, is the pivot on which the rest of this story rests. Before March 2015, Ceres was a point of light in a telescope, a blur in the best images we could manage from Earth's orbit, a known mass in a known place with known orbital characteristics, and a density that raised questions no instrument at our disposal could definitively answer. After March 2015, it was a world, a mapped, photographed, measured, chemically analyzed world. A world with craters and mountains and salt patches and a dark grey surface so ancient and so complex that the scientists receiving Dawn's data spent years picking through what it told them, publishing findings in journals and revising interpretations, and discovering, repeatedly, that the picture was stranger and richer than even the most optimistic models had suggested. Dawn entered a series of successively lower orbits, spiraling inward like a stone dropping through water in slow motion. It mapped the entire surface from high altitude, then descended and mapped it again with greater resolution, then descended further still, closer and closer to the ground, until in its final campaign it was skimming Ceres at an altitude of roughly 35 kilometers. Approximately 22 miles, close enough that if you could stand on the surface and look up, you would see the spacecraft passing overhead within a few minutes. A moving point of light against a sky that holds almost no other light at all. Because Ceres has no significant atmosphere to scatter the sun, and the sun itself, from there, is small and cold and far away. From that 35-kilometer altitude, Dawn's instruments looked down at everything. They looked down at the craters, the ridges, the flows of material that had resettled after ancient collisions, the dark plains and the darker hollows, and the bright, inexplicable patches that from the moment of first detection had made Ceres unlike anything else in the belt. And from that altitude, from that closeness, the data that came back to Earth began to assemble itself into a picture that nobody, Not even the scientists who had spent careers arguing that Ceres was different, that Ceres was interesting, that Ceres deserved more credit, had quite prepared themselves for. What it told them, in the end, is what we are building toward. Slowly, together, but understand what it took to get there. Understand that this was not a brief encounter, not a flyby where the spacecraft skims past and collects a few hours of data and continues on its way. Dawn orbited Ceres for more than 3 years. 3 years of continuous observation. 3 years of mapping and spectrometry and gravity modeling and camera passes and instrument readings building into a dataset large enough and layered enough to reveal not just the surface but the interior, not just the present but the history, not just the features but the mechanisms that produced them, and, in some cases, the mechanisms that are producing them still. The mission ended in the autumn of 2018. Not because the science was exhausted, because the spacecraft was. Dawn ran out of hydrazine, the fuel used not for propulsion, but for attitude control, for pointing, for the small thruster firings that kept its instruments oriented toward their targets and its antennas aimed back toward Earth. Without attitude control, the spacecraft became a drifting archive. Its data transmission had already long since ended. Its cameras and spectrometers fell silent. And Dawn, having spent its last drops of the fuel that had let it turn and look and speak to us, simply continued in the orbit it held, silent, stable, patient, going nowhere new. It will stay in that orbit for decades. The calculations suggest it will remain there for at least 50 years, perhaps much longer, before any chance of surface contact. There is no active systems failure to cause it to tumble out of control and fall. It simply drifts. A machine the size of a small car, its solar panels still spread wide, but receiving no command. Orbiting a frozen-over relict ocean at 35 kilometers or something not far from that, going around and around Ceres in the dark of the asteroid belt, in the cold, in the silence that is the normal condition of everything out there. It is, in a way, the most fitting monument to Ceres that we could have left. A dead spacecraft in a stable orbit, keeping a kind of permanent vigil over a world that also keeps things, that holds its ocean in suspension, that tends its frozen waters beneath a surface as dark as the space around it, that keeps its salt deposits fresh and bright inside a crater, where nothing should still be fresh, nothing should still be arriving from below. Both of them waiting. Both of them unchanged, in their different ways, by the passage of time. One of them made of metal and silicon, and the memory of human engineering. One of them made of rock and ice, and the long, slow chemistry of a solar system that is 4.5 billion years old, and, in at least one small corner, not entirely done. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. And we return now, quietly, to the thing at the center of all of it. We return to the light, to that patch of brilliant white inside Occator crater, to what Dawn's instruments found there, to what it means, to the slow unfolding argument that has been building in planetary science ever since. The argument that says Ceres is not what the asteroid belt suggested it was, not a leftover, not a ruin, not a frozen record of something that once was and is no longer. The argument that says it is something stranger. Something that still, even now, is not entirely finished with what it was doing when the solar system was young. But that argument rests on chemistry, on specific molecules, on the identity of a particular salt, found for the first time off the surface of Earth, sitting in a crater that should have been geologically quiet for millions of years, and is, as best we can tell, not quiet at all. And to understand why that salt is so remarkable, you need to understand what it means for something to be unstable, not politically, not structurally, but chemically. You need to understand what it means for a substance to have a clock built into its molecular architecture, a clock that runs in one direction and does not pause. And we will come to that now, as gently and as precisely as the evidence itself demands. Hydrohalite. That is the word. That is the specific salt, the exact molecular compound. That makes Cerealia Facula something other than a mere curiosity. And the reason it matters has nothing to do with its brightness, with the way it caught sunlight and puzzled astronomers and generated headlines for years before any spacecraft came close enough to say what it actually was. The brightness is, in a sense, the least interesting thing about it. What is interesting, what is in fact extraordinary, is what this particular compound does when left alone. Sodium chloride dihydrate, that is the formal name. 2 water molecules bound to 1 unit of sodium chloride, the result of salt crystallizing out of a brine under very specific conditions of temperature and concentration. And here is the problem. The beautiful, structurally illuminating problem. Hydrohalite is not stable under the conditions that exist on the surface of Ceres. It is not stable in the sense that it does not remain what it is. The bond between the salt and those water molecules is not permanent. Exposed to the vacuum and the radiation and the slow cycling of temperature that defines life on the surface of a small, airless body in the inner solar system, hydrohalite dehydrates. It loses its water. It reverts, molecule by molecule, to ordinary halite, plain, anhydrous sodium chloride, the kind of salt that neither glows nor tells you anything remarkable about the interior of the world beneath it. And this process does not take geological time. It does not require millions of years to run to completion. The estimates, and they are, it must be said, model-dependent estimates, worked out from laboratory measurements of dehydration rates under conditions as close as we can construct to those of Ceres's surface, place the timescale at years. At most, centuries, which means that hydrohalite detected at Cerealia Facula, photographed and spectrally identified by Dawn's instruments during its closest approaches, did not arrive from some ancient eruption buried deep in Ceres's history. It arrived recently. In the language of planetary geology, where 1,000,000 years is barely a breath, recently means something very particular. It means the brine that carried it upward was moving through Ceres's interior on a timescale that overlaps, in all likelihood, with the last moment in which the solar system has been recognizably itself. That is the clock. That is what makes the facula not merely bright but diagnostic, not merely beautiful but argumentative. The hydrohalite is evidence still in the process of eroding, and the fact that it has not yet eroded tells you something about when it stopped being delivered. It is the equivalent of finding wet footprints in a corridor and concluding not simply that someone has walked through recently, but that they may still be walking. Somewhere below the crater floor, below the cracked and frosted surface of Occator, brine is either still moving or has stopped moving so recently that the molecular evidence has not yet caught up with the cessation. And Occator crater itself demands attention here, because the crater is its own strange argument. It formed approximately 20 million years ago, the result of an impact substantial enough to excavate a basin roughly 92 kilometers across. That is a significant impact. And 20 million years, in planetary terms, is not long, but it is long enough, under normal geological circumstances, for a crater to settle into stillness, for any heat generated by the impact to have dispersed, for the surface to have equilibrated with the cold quiet of the belt, and for whatever volatile material was disturbed by the collision to have either escaped or refrozen into immobility. 20 million years should be enough time for Occator to have become an ordinary scar, a feature of historical interest rather than chemical urgency. But the salt is not 20 million years old. The dating of the bright deposits, worked out from the freshness of the material, from the way it sits atop other features, from its spectral and structural properties, places it at roughly 2 to 4 million years. Maybe somewhat younger. The crater is old, the salt is young. Something kept producing brine and pushing it upward long after the impact itself should have gone quiet. Something in the deep interior of Ceres is still warm enough, still pressurized enough, still active enough to be driving fluid toward the surface in a crater that by rights should have sealed over and gone to sleep. That something is the reservoir. Not a small melt pocket, not a thin layer of ice softened by some local anomaly, but a structure that gravity and shape modeling suggest is roughly 40 kilometers deep and hundreds of kilometers wide. A regional body of liquid, dense with dissolved salts, sitting beneath the surface of a world barely 940 kilometers across. This is not trivial. 40 kilometers is approximately the depth at which the brine is insulated from the temperature swings of the surface, protected by the overlying rock and ice, kept in a liquid state not by internal heat alone, but by chemistry, by the specific antifreeze properties of the salts and ammonia compounds dissolved within it. This is the other part of the argument, and it is easy to miss if you think of ocean worlds only in terms of heat. Europa keeps its ocean liquid because Jupiter pulls at it gravitationally, generating friction, generating warmth. Enceladus does the same in its orbit around Saturn. Ceres has no giant planet reaching down into it with tidal forces. It is too small to retain much of the primordial heat of its formation. It should, by the simple logic of size and distance and time, be frozen solid. And yet, salt and ammonia, dissolved in sufficient concentration, can depress the freezing point of water to temperatures far below 0 degrees Celsius. Not by a few degrees, by tens of degrees. A sufficiently briny mixture under the right conditions will remain liquid at temperatures that would freeze pure water many times over. This is not theoretical, it is the physical chemistry of cold brines, observed in terrestrial analogues, extended carefully by modelling to the conditions of Ceres' interior. The reservoir 40 kilometers down does not need to be warm. It needs to be salty enough, and dense enough and deep enough to be shielded from the worst of the surface cold. And Ceres, which is approximately 1/4 water by mass, which holds, locked in its ice and brine, more fresh water than every river and lake on the surface of the earth, has salt and volatiles in sufficient supply to sustain exactly this kind of chemistry. More fresh water than all of Earth's rivers and lakes. It is worth holding that for a moment against the image of Ceres as the solar system's most unremarkable body, the runt of the belt. The world nobody thought to look at closely until a spacecraft was already en route. The volume of water implied by that rough fraction, roughly 1/4 of Ceres's total mass, is staggering relative to what we think of when we think of an asteroid, even a large one. The inner solar system, the dry part, the rocky part, the region where we live and where every conversation about life begins, contains a world soaked with water. Hiding it beneath a surface, dark as asphalt, cold as the space between worlds. Lit only by two patches of salt so brilliant they earned the name little torches. The name came from Latin. Facula, faculae, for the plural. Little torch. Little torches. Cerealia facula, for the central bright mass at the heart of Occator, named for the goddess herself. Vinalia faculae, for the scattered eastern patches, named for the Roman wine festival. A detail that carries its own quiet absurdity, the idea of harvest and wine and celebration attached to a patch of brine salt on a body 400 million kilometers from the nearest vineyard. But the Romans who gave the goddess her name, who built the festivals around her, who understood that the word cereal came from Ceres, from the grain she governed. From the agricultural abundance she embodied, they could not have known that her namesake harboured an ocean, that the goddess of harvest was keeping, somewhere beneath her frozen skin, something more fundamental than wheat. Water, the precondition for everything the harvest represents. Dawn found the salt in 2015, and the implications built slowly, paper by paper, over the years that followed. As the data was examined and re-examined, and the instruments coaxed to yield everything they had captured in those final close passes. But there was a second line of evidence, entirely independent of Occator, entirely independent of the Faculae, built not from chemistry but from geology. And it was standing alone on the surface, 4 kilometers tall, waiting. The mountain would wait. 4 kilometers of it, patient in the dark, geologically young and strangely fresh, keeping its secret in plain sight for anyone who cared to look. But before that story could be told, before the mountain's solitude could be explained, there was a chemistry problem to solve. And the chemistry problem was this. What, exactly, was the bright material? Not in the loose, headline sense, not salt in the same way you might say the ocean is salty, a word that covers everything and explains nothing, but in the precise, compound level, molecular sense that matters when you are trying to read a world's interior from its surface. Because the instruments on Dawn were not vague. They were not producing impressions or estimates or hopeful guesses dressed as data. They were reading the spectral fingerprints of specific molecules, the way each compound absorbs and reflects particular wavelengths of light, in patterns so characteristic they function as a kind of chemical signature. And the signatures coming back from Cerealia Facula and Vinalia Faculae were clear enough that the science team could name what they were looking at with confidence. The dominant material was sodium carbonate. NaCO, in the notation chemists use, though the notation matters less than the substance itself, a bright white salt that forms when sodium-rich water evaporates and leaves its solutes behind, the way a tide pool on Earth leaves rings of white crust around its edges when the sun hits it in the afternoon and the water slowly goes. Sodium carbonate is familiar chemistry. It is the active component in washing soda, used in glass making, found in dry lake beds on Earth, where ancient seas pulled back and left their mineral memory behind. It is, in other words, precisely what you would expect to find at the site of evaporating brine. The presence of sodium carbonate at Cerealia Facula was not merely consistent with the idea that salty water had reached the surface of Ceres. It was, in a very real sense, the signature of evaporating brine, the residue, the calling card, the chemical remains of a process that requires liquid water to function. And the concentration was extraordinary. Models of what Dawn's instruments were measuring suggested that the sodium carbonate at Occator represented one of the largest concentrations of carbonate minerals anywhere outside Earth. Not a trace detection, not a faint smear at the limit of the spectrometer's sensitivity, but a genuinely massive deposit, bright enough to be visible from orbit against the deep grey of Ceres's surrounding surface, prominent enough to earn names of its own, the little torches, Cerealia and Vinalia, blazing against a background darker than old asphalt, and doing so because of the sheer quantity of reflective white salt left behind when brine came up from below and met the cold vacuum above. But sodium carbonate, on its own, carries a limitation as evidence. It is stable. Once the water evaporates and the salt crystallizes, sodium carbonate can persist for a very long time under the right conditions. It tells you that brine was present at some point, but not necessarily recently, not necessarily within any useful window of time. A geologist looking at sodium carbonate alone cannot easily tell you whether the brine that created it arrived 3 million years ago or 3 billion. The clock is there, but it runs slowly, and under some conditions hardly seems to run at all. The second compound changed everything, and the second compound was hydrohalite. Hydrohalite is sodium chloride dihydrate. NaCl2HO, if the formula helps to anchor it, ordinary table salt, sodium chloride, but with 2 water molecules locked into its crystal structure, held there by the specific conditions under which the salt crystallized from cold brine. If you have ever seen salt at very low temperatures form unusual crusts, crystallize in unexpected shapes, behave differently than it does in a warm kitchen, you have encountered the beginning of what happens when salt forms in the cold rather than the heat. Hydrohalite is the cold brine version of salt, and it is radically unstable once it is no longer in the cold brine environment that made it. At the temperature and pressure conditions on Ceres's exposed surface, hydrohalite dehydrates. It loses its 2 water molecules. The crystal structure that required them collapses into something simpler, something that requires no water to maintain, and the material that was hydrohalite becomes ordinary halite, plain salt, anhydrous, dry, stable. This process happens across a range of timescales depending on temperature and other local conditions, but the range is not geological. It is not millions of years. The conversion from hydrohalite to halite, under the kind of radiation and vacuum exposure the surface of Ceres provides, happens on the order of years to at most centuries. Perhaps decades. Perhaps a few hundred years in unusually sheltered conditions. But not millions of years. And certainly not the 20 million years that Occator crater has been sitting there, dark and cold and apparently quiet. Dawn detected hydrohalite at Cerealia Facula, the first detection of this specific hydrated salt anywhere off Earth. The first time the compound had ever been confirmed to exist in any solar system body other than our own. And the implication of its presence was immediate and logical and not subtle once you understood what the compound's stability window actually was. The hydrohalite at Cerealia Facula had not been sitting there since the impact that formed Occator. It could not have been. The physics of its decomposition would not permit it. If the hydrohalite had arrived 20 million years ago, it would be gone now, converted long since into plain anhydrous salt, with no trace of the water molecules it once held. The fact that it was still there, still hydrohalite, still retaining its water molecules in the crystal lattice, meant it had arrived recently, Not in a geological sense where recently means 10 million years, but in the more demanding sense where recently means within a time window measured in thousands to hundreds of thousands of years at the outside, possibly far shorter than that. The Hydrohalite was a clock, and the clock was still running. Think of it this way. Imagine you find a piece of ice sitting on a warm sidewalk in the sun. You do not need to know when the ice was placed there to understand one thing immediately: it was placed there recently. Because ice melts. If it had been there for 3 hours in this heat, it would already be a puddle. The fact that it is still ice tells you that its presence in this warm, hostile environment is recent, is ongoing, or both. Hydrohalite on the surface of Ceres is the same kind of argument, just played out over a longer timescale and with different physics. The compound is chemically unstable in the environment where Dawn found it. That it still exists tells you it arrived recently. That it exists in quantity tells you the process that brought it up was substantial, not a microscopic trickle, but something capable of depositing a detectable, measurable concentration of a fragile compound before the environment could destroy it. And here the question pivots naturally from what to how. If hydrohalite, this delicate, water-laden, environment-sensitive salt, was deposited at Cerealia Facula within the last few years to centuries, then something was transporting brine to the surface of Ceres within the last few years to centuries. The compound is a symptom. The disease, if that word can be used loosely, is liquid water moving through the interior of what most people had dismissed as a large, grey, geologically inert rock between Mars and Jupiter. The dating of Occator's bright material made this more precise and more striking. Occator crater itself is roughly 20 million years old. Whatever impact formed it, and it would have been a substantial one, to gouge out a hole 92 kilometers across in the crust of a world 940 kilometers in diameter, that impact happened 20 million years in the past, which in the context of the solar system's 4.5 billion year history is not especially old, not primordial, but old enough that you might reasonably expect the crater to have settled into a quiet geological retirement, its walls slowly eroding under the micrometeorite bombardment that patiently reworks every surface in the belt, its floor accumulating the fine grey dust that covers everything on Ceres, its chemistry long since stabilized. The salt at Cerealia Facula, analysed carefully from Dawn's data, is estimated to be only roughly 2 to 4 million years old. Not 20 million. Not 20 million years old, with a little extra brine from the original impact trickling in over the subsequent ages. 2 to 4 million years, a fraction of the crater's age. The crater formed 20 million years ago, and then, millions of years later, long after the initial upheaval of the impact should have subsided, and the crust should have resealed itself, and any impact-driven melting should have refrozen, something was still pushing brine up through the floor and depositing it at the surface. The crater kept bleeding long after the wound should have healed. This temporal gap, the 20 million year old bowl containing 2 to 4 million year old salt, is one of the things that makes Occator so compelling as evidence. Because it eliminates the simplest alternative explanation that the bright material is just the aftermath of the impact itself, the excavated interior brought to the surface during the collision. The subsurface brines flash melted and splashed outward and then refrozen. If that were the explanation, the salt and the crater would be roughly the same age. They are not, by a factor of roughly 10. Something was operating inside Ceres, pumping brine toward the surface through Occator's floor, millions of years after the impact had come and gone, and the immediate thermal pulse of the collision had faded. And so the question shifted. Not what, not when, but where was it coming from, and why had it not all frozen? The gravity and shape data that Dawn collected, painstakingly built up over the spacecraft's successive lower orbits, measuring the subtle variations in the gravitational field as Dawn passed overhead, and these variations tugged gently on its trajectory, pointed toward a structure beneath Occator that was doing the work. The models built from this data described something large. Not a small melt pocket, not a local anomaly created by the impact, but a regional body of dense, salty liquid sitting tens of kilometers below the crater floor and stretching hundreds of kilometers in extent beneath the surface. 40 kilometers deep, hundreds of kilometers wide. A reservoir, in the language of the scientists who modeled it. That was not a laboratory vial of liquid hidden in the rock, but something with the horizontal scale of a shallow sea and the vertical depth of a respectable mountain range measured from top to bottom. A regional brine sea sitting beneath the ice and mud and rock of Ceres's outer shell, dense with dissolved minerals, insulated from the cold above by the sheer thickness of everything above it, and apparently still connected by some network of fractures or conduits, or simply by the pressure dynamics of a deep, heavy liquid body to the surface of Occator crater. The connection is not perfectly understood. The exact plumbing, the specific pathways by which brine reaches the surface of Cerealia Facula from a reservoir 40 kilometers below, is not mapped with the precision of a pipe diagram. Ceres did not leave us a cross-section. But the evidence that the connection exists is the brine salt itself, sitting at the surface where it has no business being unless something brought it there from below. The reservoir is the source, the faculae are the exit points. The hydrohalite's youth is the timestamp on the most recent delivery. And now the third question, why has it not frozen? Why is any of it still liquid at all, 40 kilometers below the surface of a body roughly 940 kilometers across, orbiting the Sun at a distance of between about 2.5 and about 3 astronomical units, a world that receives barely a tenth as much solar energy per unit area as Earth does? A world whose surface temperature hovers around -100 degrees Celsius in the sunlit zone and far colder in shadow. A world whose internal heat from the decay of radioactive elements is a fraction of what larger, rockier bodies produce. The answer is antifreeze. Not antifreeze in the automotive sense, not ethylene glycol in a bright green bottle, but the same underlying physical principle applied to the chemistry of a world that has been slowly mixing its ingredients for 4.5 billion years. Antifreeze works by interfering with the formation of ice crystals. Pure water freezes at 0 degrees Celsius because that is the temperature at which water molecules lose enough energy to lock themselves into the rigid lattice of an ice crystal. Dissolve something in the water, anything, in principle, but salt is particularly effective, and you disrupt the geometry. The foreign molecules get in the way. The ice crystals cannot form as easily. The freezing point drops. Concentrated salt water freezes at temperatures well below 0. More concentrated solutions freeze at even lower temperatures. And if you add ammonia to the mixture, which Ceres appears to have done, ammonia-bearing compounds having been detected at its surface, you push the freezing point down further still. Ceres is thought to have incorporated substantial quantities of ammonia into its interior during its formation in the outer reaches of the early solar system, where ammonia was abundant in the same icy material that built it. And the salts, the sodium carbonate, the chloride salts, the carbonates, are present in abundance, as the Faculae themselves prove. The brine reservoir 40 kilometers down is not pure water. It is a rich, cold, mineral-laden solution, heavily salted and almost certainly laced with ammonia-bearing compounds, and this chemistry means that what would freeze into solid ice at 0 degrees Celsius is instead still a liquid at temperatures far below zero. The antifreeze chemistry is the physical reason that a body this small, this cold, this far from the sun, and this old can still harbour pockets of liquid water at all. It is an elegant kind of survival. Not warmth, exactly, not the tidal flexing that keeps Europa's ocean churning beneath its ice shell, Jupiter's gravitational grip, squeezing the moon's interior like a fist squeezing a wet sponge. Ceres has no giant planet pulling at it in that way. What Ceres has instead is chemistry, the slow, mineral-rich, ammonia-touched chemistry of a world that was built from the right ingredients in the right proportions to suppress its own freezing. To keep the brine liquid not because it is warm, but because the brine itself is engineered by its dissolved contents to resist the cold. The ice has been advancing on this ocean for billions of years. The chemistry has been pushing back and losing slowly, and the result is what we have now. A largely frozen world with pockets of dense, cold, mineral dark liquid surviving in the spaces between. The word relict appears in the scientific discussions of Ceres's interior in a precise sense. A relict is what remains of something that was once larger, once more extensive, now reduced but not entirely gone. A relict ocean is not a healthy, intact ocean. It is the last of something, the remainder of a global body of water that once covered more, went deeper, moved more freely, and has since been progressively claimed by ice until only the most chemically resilient, the most antifreeze-laden, the most salt-saturated pockets remain. Ceres is, in this reading, a dying sea. The dying is not fast, it is not catastrophic, not dramatic, not visible on any human timescale. It is glacially slow, in every sense of that word. But the direction of travel is clear, and the Faculae in Occator, bright and young and made of salt that should not still be there, are the evidence that the process has not finished. The sea is still losing ground, the salt keeps coming up, the clock keeps running. There is one more piece of the Occator story that deserves to be mentioned, though with the caution it requires. During some of Dawn's observations, a faint haze was reported over the bright spots at certain local times of day, the equivalent of morning on Ceres, when the sun first strikes the Faculae and the temperature at the surface rises slightly. A faint, diffuse brightening above the deposits, consistent with ice or water vapour sublimating off the surface, and briefly creating something that looked, in the data, like a very thin, transient atmosphere confined to the region of the bright patches. The haze, if it is real, would fit. It would fit the picture of ongoing brine delivery from below, brine that reaches the surface and partially evaporates in the light, the water component rising as vapour and then freezing out again in the cold of Ceres's night or dissipating into space. The salt component remaining behind, accumulating slowly over thousands of years into the bright deposits Dawn photographed. It would make the Faculae not just the record of past events, but an active process, something still happening, something that, if the instruments had been watching on the right morning, at the right angle, with the right sensitivity, might have been seen in the act. But this observation is less certain than the salt chemistry. The haze detection rests on a smaller body of data and is more susceptible to instrumental effects and observational geometry than the clear spectral signal of sodium carbonate and hydrohalite. The science team noted it. The scientific literature on Occator discusses it, but it is held at a different level of confidence than the compound identification, a suggestive detail, a piece of evidence that would strengthen the picture if confirmed by future observation, but not the load-bearing beam of the argument. The load-bearing beam is the hydrohalite. The haze is additional texture, a hint, a possible glimpse of the process caught mid-act. Worth knowing, worth remembering, but flagged honestly as less certain than what the spectrometer said. What the spectrometer said was this: on the floor of a crater 20 million years old, on the darkest world in the inner solar system, darker than old road tar, darker than weathered coal, reflecting back only about 9% of the light that hits it. There are two patches of bright white salt, so concentrated and so reflective they appeared, in early images, as something almost luminous against the surrounding grey. They are not luminous, they do not produce their own light, but they are fresh, and they are specific, and they contain a compound that dehydrates within years to centuries under these conditions. They are, in the careful language of planetary science, evidence of geologically recent brine exposure at the surface. They are, in the simpler language of what that actually means, the chemical signature of a sea that is not entirely dead, left by water that found its way up through 40 kilometers of rock and ice, and emerged into the vacuum of space at the bottom of an ancient crater, and left its minerals behind when the water itself evaporated into nothing. Cerealia Facula. The little torch. Named for the harvest goddess who, across 400 million kilometers of space and 4.5 billion years of history, turned out to be keeping something far older than grain. And then there is the shape of the reservoir itself, and what it implies about Ceres's interior more broadly. Because 40 kilometers down and hundreds of kilometers wide is not a small feature. It is not a localized melt pocket created by the Occator impact and maintained by residual impact heat slowly bleeding away. The scale of what gravity modeling implies is regional. It is subsurface. And it is, when you set it alongside everything else Dawn measured, the density, the water mass fraction, the spectral signatures of ice and hydrated minerals across the surface, the detection of sodium carbonate not only at Occator, but at other locations on Ceres in smaller amounts, the broader pattern of a world that is far less dry than any ordinary asteroid has any right to be. Consistent with the picture of a body that was, in its early history, essentially an ocean world. Not an ocean world like Earth, with liquid water at the surface and sunlight warming it from above. A colder kind of ocean world, kept liquid internally by the heat of a young, still-forming, radioactively warm interior, accreting ice and rock together in the outer solar system before something. The gravitational turmoil of Jupiter's formation, the chaotic dynamical reshuffling of the early solar system, scattered the material it would have needed to keep growing and left it stranded, alone, in the belt. A planetary embryo. Not a failed planet, exactly, because failure implies that it tried to become something and did not make it. When the more honest description is that the conditions for its continued growth were taken away from the outside, not lost from within. It was building toward something, and the building stopped, and what remains is what it was at the moment the building stopped, differentiated already, with a rocky interior and a water-rich outer shell. warm enough in its youth to have maintained a global ocean for perhaps millions of years, and now cooling, slowly, inexorably, the ocean retreating into ice, except where the chemistry holds it back. The reservoir beneath Occator is, in this reading, a remnant, a surviving pocket of what was once, billions of years ago, a much larger body of liquid. The brine that is pushing up through Occator's floor today is the last of something immense that was once present across much of Ceres's interior, reaching now through the fractures and conduits that remain open, finding the path of least resistance toward the surface, and leaving its chemical signature in the form of two bright, fresh, transient salt patches in the middle of the darkest crater floor you have ever seen. The crater kept bleeding. And the reason the crater kept bleeding, long past the point where any impact-driven process could explain it, is that what it is bleeding is not the remnant of an impact at all. It is the remnant of an ocean, a dying ocean, a frozen one, a mostly frozen one, but not entirely gone, not entirely still, not entirely silent. And the evidence that it is still partially alive is the salt itself, white and bright and chemically fragile, sitting on the surface of Ceres like a letter addressed to anyone who came close enough to read it. Dawn came close enough. In its final low-altitude campaign, spiraling down to within about 35 kilometers of the surface, close enough that if Ceres had had the kind of thin atmosphere Mars has, the spacecraft would have been skimming through it. The cameras and spectrometers captured the Faculae in more detail than had ever been possible from farther away. The images from that altitude show the texture of the deposits, the way the bright material is concentrated in the central pit of Cerealia Facula, the floor of the innermost structure at the heart of the crater, and spreads in the scattered, less coherent pattern of Vinalia Faculae to the east. The way the bright material is not uniformly distributed, but shows internal structure, brighter patches and slightly less bright patches, the product of multiple episodes of brine emergence rather than a single event. The way the surrounding crater floor is nearly black, and the contrast between that darkness and the bright salt is so extreme that, in the images, the Faculae do look, not luminously, not literally, but in terms of their tonal relationship to everything around them, like something burning, like torches, like two small, improbable fires lit inside a very old and very dark room. And somewhere below, 40 kilometers down, sitting in the cold and the pressure and the mineral-rich stillness of a partially frozen sea, the brine that made them continues to exist. Whether it is moving right now, whether brine is this very moment making its slow way upward through conduits in the crater floor, whether the haze that may or may not have been detected will one day be confirmed as the surface expression of an ongoing upwelling. These questions the data can only partially answer. And they are the questions that make Ceres not a closed case, but an open one. Not a museum exhibit of past activity, but a world where the past and the present are, in the geology of salt and brine and fractured ice, still tangled together in ways that would require another mission. Better instruments, perhaps a lander sitting directly on the floor of Occator, to fully distinguish. Dawn is not coming back. It ran out of the hydrazine propellant that kept its attitude control thrusters firing, the fuel that let it point its instruments and antennas and solar panels in the right directions in late October of 2018. Without hydrazine, it could no longer maneuver, and it went dark. It is still up there, still in orbit around Ceres. its trajectory stable enough that models predict it will remain in that orbit for decades before any natural perturbation might bring it down. A silent, orbiting monument. The spacecraft that answered some of the oldest questions about the asteroid belt's largest body, that found the salt and read the chemistry and measured the gravity and photographed the little torches from 35 kilometers away, is now as inert as the crater floor it spent its final months mapping. But the questions it left open have weight. The brine reservoir modelled from its gravity data. The hydrohalite clock running on Cerealia Facula's surface. The depth and extent of what may be one of the closest ocean worlds to the Sun. These are not answers that require speculation or extrapolation beyond what the data says. They are inferences, yes, models are models, and the exact dimensions of the reservoir and the exact age of the deposits carry uncertainties that the scientists who built those models would be the first to acknowledge. But they are inferences grounded in real instrument data from a real spacecraft collected during real passes over a real world that was for 3 years, the most closely observed body in the asteroid belt. And there is a second line of evidence, an entirely different kind of evidence, built not from spectrometers reading the chemistry of a crater floor, but from topography, from the shape of the surface itself, from the existence of a single mountain that stands alone on a world where it has no obvious reason to stand, and from what the physics of ice and gravity and time suggest about why that mountain is so conspicuously, surprisingly, almost suspiciously alone. The mountain had been waiting. 4 kilometers of ice and salt and slush, frozen in the shape of something that erupted from below, its sides steep and bright and uneroded, rising out of the grey plane of Ceres's surface like something that had no business being there and knew it. Ahuna Mons, still standing, still young, geologically speaking, in a world where almost everything else had either been worn away or slumped back toward the ground under the slow, patient pull of its own weight over hundreds of millions of years. The question Ahuna Mons was asking, and it was asking it clearly, to anyone with an instrument capable of seeing it, was not only what it was. That was answerable. It was a cryovolcano, an ice volcano, a structure built not from molten rock, but from the cryovolcanic equivalent, a slush of ice and brine and salts pushed from below to above and frozen in place on arrival. The question it was asking was deeper than that, and stranger. It was asking why it was alone. On any other kind of world, a single mountain standing alone in the middle of a plain would not be the strange thing. Mountains stand alone all the time. Volcanoes rise from the surrounding landscape in isolation, built up over thousands of years of eruption and cooling, and the surrounding terrain shows no corresponding structure because the eruption was local, confined, a single vent pushing material upward in one place, while the rest of the surface stayed quiet. There is nothing inherently suspicious about a solitary peak. But Ceres is not any other kind of world. And the reason Ahuna Mons is suspicious, genuinely, measurably, scientifically suspicious, is not that it exists, it is that nothing else does. If cryovolcanism were a one-time accident on Ceres, a single improbable event that happened once and never repeated, you might expect one mountain, one structure, one place where the internal pressure found a weakness in the shell above it and pushed through, and then sealed itself, and that was that. One mountain standing alone would be consistent with a one-off. Unusual, yes, but not inexplicable. The problem is the math, and the physics, and what happens to ice over time. Ice, it turns out, is not the rigid, permanent substance it feels like when you hold a piece of it in your hand. At the scale of a mountain, over the scale of hundreds of millions of years, ice behaves less like a solid and more like a very, very slow liquid. It flows, it creeps. Under the pressure of its own enormous weight pressing downward, and under the gentle, relentless influence of gravity pulling every molecule toward the center of the world beneath it, an icy dome does not simply sit there indefinitely, unchanged. It spreads. It flattens. Over hundreds of millions of years, a structure that was once a tall, steep-sided mountain gradually smears itself across a wider and wider area, its peak dropping and its flanks spreading until what was once a recognizable volcanic cone becomes something much harder to see, a broad, shallow, barely elevated swelling in the surface, a ghost, a memory of a mountain rather than a mountain itself. This process has a name: viscous relaxation. The word viscous comes from the same root as the word for thick, slow-moving fluids, the same root that gives us the word for honey or syrup, substances that pour but do so slowly, reluctantly, as though they remember being solid. And that is almost exactly what happens to an old icy dome on Ceres. It relaxes. It settles, it loses its shape and spreads into the surrounding terrain until it is nearly invisible to an instrument trying to map topography from orbit. The extraordinary implication of this is that Ceres should be covered in ghost volcanoes. If cryovolcanism has been operating on this world throughout its history, and the internal heat budget, the salt chemistry, the reservoir models all suggest that it has been, not once but repeatedly, at an estimated average output large enough to be geologically meaningful, then the surface of Ceres should be littered with the flattened, barely detectable remains of dozens or hundreds of ancient cryovolcanic structures, spread and softened by hundreds of millions of years of viscous relaxation into shapes that only the most careful topographic analysis could reveal as what they once were. And when the Dawn science team looked for exactly that, when they applied the right analytical tools to the careful maps the spacecraft had made of Ceres's surface, that is what they found. Not a world that had erupted once and fallen silent. A world scattered with the softened remnants of its own earlier eruptions. A planetary surface written over and over by the same process, each successive chapter slowly erasing the one before it. Ghost volcanoes. Ancient, flattened, still faintly present in the topographic record, visible not as mountains but as subtle variations in elevation that only make sense if you know what to look for and why. Ahuna Mons is not alone because cryovolcanism happened only once on Ceres. It is alone because it happened recently enough that the physics of viscous relaxation has not yet had time to flatten it. Its older siblings are still there, in a sense. They are simply no longer standing. They have become part of the grey plane itself, absorbed back into the surface they rose from. Their identities dissolved by time and gravity into something that requires careful science to detect, rather than simple observation to see. Ahuna Mons is the young one, the fresh one, the one that erupted late enough in Ceres's history that the slow erasure has not yet claimed it, and that freshness is itself information. It tells you something about when the internal plumbing of this world was last active. It tells you that the ocean below, the relict sea, the pockets of dense, salt-laden brine resisting the freeze that has claimed most of their neighbours, was not only producing salt-heavy outflows that climbed toward Occator's floor. It was also, at some point in the geologically recent past, generating enough internal pressure and heat to push material up through the overlying crust and pile it into a mountain 4 kilometers tall. The two lines of evidence, the chemistry of the crater and the topography of the mountain, are independent of each other. They were discovered by different instruments, they were analyzed by different methods, and they point separately to the same conclusion. Something has been moving inside Ceres. Something is, in all reasonable probability, still moving. But there is a third line. And it came before either of those, before dawn had even reached Ceres, from an entirely different kind of observatory looking at this small distant world through the longer wavelengths of infrared light. The Herschel Space Observatory, a European facility, a large infrared telescope that operated in space from 2009 until it ran out of coolant in 2013, turned its instruments towards Ceres in 2014 and detected something that asteroids are not supposed to emit. Water vapor. Not ice. Not the spectral signature of frozen water sitting still on a surface. Active water vapor, outgassing from the surface of a body that the conventional classification system had long since decided was simply a large, inert rock, tumbling quietly between Mars and Jupiter. The detection was careful. The Herschel team was cautious about it, appropriately so, because the claim was unusual and the implications were significant, and good science does not announce unusual things casually. But the signal was real. Two localized sources associated with the sunlit side of Ceres, consistent with sublimation, ice turning directly to vapor in the warmth of sunlight. Or possibly with something more active, something more like venting from below. The mechanism was debated. Whether the vapor was coming from surface ice exposed in a shadowed region, then warmed by the sun, or from something deeper pushing volatiles upward, was not something Herschel could definitively resolve. The telescope could tell you the vapor was there. It could not tell you exactly why. But the presence of the vapor was itself the startling thing. An asteroid was breathing, not in the literal, biological sense of that word, but in the sense that something inside it or on it was actively releasing water into space in a detectable, measurable stream, behaving not like an inert stone, but like a comet, like a volatile, rich body, with something still happening inside it or at its surface, something dynamic rather than frozen in the past. When dawn arrived at Ceres in March 2015 and began to map the surface in detail, the question of what Herschel had been detecting became less abstract. The answer, which would take years of analysis to fully assemble, was larger than anyone had anticipated. The vapor was not a fluke. It was a symptom. And the symptoms, taken together, were pointing at a diagnosis that the conventional picture of the asteroid belt had never made room for. Near Ernetot crater, in the northern hemisphere of Ceres, Dawn's instruments detected something else entirely. Something that does not need to involve liquid water or internal heat or volcanic processes to be significant, though it is more significant in the presence of all three. Aliphatic organic compounds, carbon-hydrogen chains, the molecular building blocks that carbon chemistry tends to build when it has the right ingredients and the right conditions and, crucially, enough time. Organics on Ceres. The word organic in chemistry means something precise and neutral. It means molecules built around carbon atoms bonded to hydrogen. The structural family of compounds that includes everything from the simplest chains of a few atoms to the vast, interlocking complexity of living cells. Finding organic compounds on a solar system body does not mean finding life. It does not imply life. It says nothing definitive about biology at all. What it says is chemistry. What it says is that the conditions on Ceres, the presence of water, the presence of salts, the presence of carbonate minerals, the presence of ammonia-bearing compounds, and now the presence of carbon-hydrogen chains add up to something that planetary scientists have a term for: a prebiotic pantry. The pantry does not cook the meal. It only has the ingredients, and whether those ingredients were ever combined in the right way, at the right temperature, with the right energy input, for long enough, in the right part of Ceres's interior, or at the right moment in its history, that is a question for which the answer is honestly, genuinely, scientifically unknown. It should not be overstated. It should not be dressed up as evidence of life, or even of life's likelihood. The finding is remarkable enough without that. What it means is that in one small, cold, dark as asphalt body orbiting the Sun between Mars and Jupiter, you have water, you have salts, you have carbonates, you have ammonia compounds, and you have organic molecules, all together, on the same world, in the same relict ocean, around the same internal heat source that is still, by the evidence of Occator and Ahunamons, generating some kind of geological activity. The assembly of those ingredients in one place is not trivial. It is not an accident that they are all there. Ceres formed in the outer part of the early solar system, where temperatures were cold enough for volatiles to condense, and then migrated or was scattered inward to its current position in the belt, carrying those cold, outer solar system ingredients with it into a warmer neighborhood it had not originally occupied. The volatiles it brought, the ice, the ammonia, the carbon compounds, were the legacy of its birthplace, preserved inside a body large enough to hold them, but small enough to cool slowly, to partially differentiate, to keep the chemistry going in quiet pockets, long after the dramatic events of the early solar system had settled into the current, apparently boring configuration we now call the asteroid belt. Ceres is not boring. It never was. It simply required the right instruments and a spacecraft patient enough to spend years spiraling down through successive orbits, getting closer and closer to a surface that looked grey and dead from a distance and turned out, on close inspection, to be a frozen record of processes that are not entirely finished. Let us be honest about what the evidence shows and what it does not. The picture that emerges from 3 years of dawn data, from the Herschel vapor detection, from the gravity modelling of Occator's reservoir and the topographic analysis of Ahunamons and its vanished siblings, is not the picture of a warm, wet, active ocean world like the young Earth or the deep-sea environments where we find life thriving in thermal vents today. Ceres is not that. It was, once, closer to that, in the early solar system, billions of years ago, when the heat of formation and the energy released by the separation of its rocky core from its icy shell were still fresh, when the global or near-global ocean that models suggest it once possessed was liquid throughout rather than mostly frozen, when the water and the chemistry and the heat were all present at once, in abundance. But that time has passed. The ocean, in the deepest sense of what an ocean is largely gone. What remains is the skeleton of it, the differentiated interior, a rocky, muddy core wrapped in an icy, salt-rich shell, not a clean separation, but the kind of intimate, well-mixed relationship that forms when rock and ice spend billions of years in proximity and under pressure. A muddy mantle where the two were never fully separated retains the echo of the ocean it used to be, in the form of dense, deeply buried pockets of brine too salty and too cold to freeze, kept liquid by the antifreeze chemistry of their dissolved salts and ammonia far below the temperatures at which pure water would have long since surrendered to the cold. The relict ocean. That is the phrase that captures it most honestly. Not an ocean in the full, present tense sense. Not a body of liquid water sitting beneath a thin ice lid in the way that Europa is modelled, or Enceladus, those outer solar system moon worlds that we speak of as the likeliest candidates in the solar neighbourhood for habitable liquid environments. Ceres is not like them, not in its current state. What it has is older and quieter and more partial than that, a dying sea caught mid-freeze. The liquid that remains concentrated and salt-heavy and cold, held in pockets and connected by channels or perhaps by slow seepage through porous rock, able under the right conditions of impact or internal stress to find a path upward and emerge at the surface as the salty, reflective, hydrohalite-bearing brine that painted the floor of Occator crater and built the Faculae that look from a dawn spectrometer a few hundred kilometers up, like two torches burning in the dark. The 2015 speculation, the public wave of what are the lights, that swept through news cycles for months before Dawn's instruments could deliver their answer, was, in retrospect, a perfectly understandable response to something genuinely unusual and genuinely unresolved in that moment. The images came back showing two bright patches on a dark world, and the answer was not yet in. People filled the gap with whatever narrative came to hand. Some suggested outgassing, some suggested exposed ice. A few, inevitably, suggested something more dramatic than either. The language of alien cities, artificial lights, evidence of something constructed rather than geological. This is what uncertainty does in the absence of an answer. It generates stories. It generates the full range of what humans are capable of imagining when they are looking at something they do not yet understand. But the answer came. It was not aliens. It was sodium carbonate and hydrohalite and the slow, patient, billions of years process of an ocean freezing in place and leaving its chemistry behind as the record of its own long dying. The alien light story is retired now, not because it was stupid to wonder. It was not stupid to wonder. It was natural. It was the right impulse of curiosity applied to a genuinely strange observation. But because the real answer is available, and the real answer is more interesting, not less. A dead civilization would have told us something about intelligence. The salt tells us something about the solar system's plumbing, about the persistence of liquid water in unexpected places, about the chemistry that preceded everything we know about the origin of life on at least one world. That is not a lesser answer. It is a deeper one. The Dawn spacecraft that gathered all of this data, that spiraled patiently inward through orbit after orbit, that spent 3 years photographing and spectroscoping and gravity mapping this small, dark, unexpectedly rich world, is still up there. It has been silent since October and November of 2018, when the last of its hydrazine attitude control propellant was exhausted and its ability to point its antenna toward Earth and its solar panels toward the Sun finally gave out, and the spacecraft simply stopped responding and became a permanent resident of the Ceres system. It is not on the surface. It did not impact. Mission planners chose its final orbit carefully, with planetary protection in mind, the requirement that spacecraft not contaminate bodies of interest for future science, and Dawn's orbit is stable enough that it is expected to remain in place for decades before any chance of orbital decay would bring it close to the surface. So, it orbits, silent, locked in a fixed attitude, no longer commanded, no longer transmitting, no longer receiving, but still moving, still following the arc that the mathematics of gravity has assigned to it over the surface of the world it spent 3 years studying. An artifact. A monument of a particular kind, not built in stone and not intended to last forever, but lasting nonetheless. There is something both melancholy and quietly right about it, a spacecraft that travelled for years to reach a place and then stayed, unable to leave, gradually becoming a small part of the environment it was sent to observe. No follow-up mission has been approved. Dawn gathered a data set that scientists are still working through, still publishing on, still extracting new analysis and new interpretation from years after the spacecraft went silent. But Ceres has no successor mission currently en route to it, no planned return visit with instruments that could go deeper, measure more precisely, answer the questions that Dawn's data raised but could not fully settle. Questions like, are the Faculae still growing? Is the brine reservoir still actively seeping upward, still refreshing the surface salt deposits with new material? Or has the most recent phase of activity wound down in the years since Dawn watched? What is the full extent of the organic compounds near Ernetit, and how are they distributed across the wider surface? What is the precise structure of the muddy interior? And how thick is the icy shell above the deepest remaining brine pockets? These are answerable questions. They are not unanswerable in principle. They require an instrument and a platform and a budget and a decision, but the science knows how to ask them and would know how to answer them with the right data. For now, they remain open. Ceres keeps its remaining secrets with the patience of a world that has been keeping them for billions of years and is in no particular hurry to surrender them to something as brief and tentative as a spacecraft that orbited for 3 years and then fell silent. And yet what Dawn did find is not a small thing. It is not a footnote in the catalogue of ocean worlds in the solar system, a list that has grown surprisingly long as planetary science has matured, as instruments have improved, as the question, where is there liquid water beyond Earth, has been asked seriously enough to look carefully for the answer. Ceres belongs. Not at the top, not as the most dramatic example, not as the warmest or the most accessible or the most liquid, but as a member of the category, as the closest ocean world to the Sun, as the one that was orbiting in the inner solar system all along, hiding in the least glamorous neighbourhood the solar system contains, while the discussion of ocean worlds focused almost entirely on the cold outer moons orbiting Jupiter and Saturn. As though anything in the middle, anything in the belt, anything between the inner rocky planets and the gas giants could not possibly be interesting in that way. Ceres was interesting in that way. It was always interesting in that way if you asked the right questions and sent the right instruments and were willing to revise the story the conventional picture was telling about what an asteroid actually is. The conventional picture said, the asteroid belt is a junkyard. Remnant rubble. Material that failed to coalesce into a planet because Jupiter's gravity kept stirring the pot, kept nudging the orbits of the belt's occupants into collision courses with each other rather than into the gentle, accumulating mergers that built the planets. Failed material. Dead material. The most boring region of the solar system, a nuisance to spacecraft trajectories, a source of meteorites, a graveyard of unrealized planetary ambitions. And in that junkyard, according to the conventional picture, the largest object, Ceres, was simply the king of the rubble, the biggest leftover. The remnant protoplanet that almost made it, that got large enough to pull itself into a sphere under its own gravity. large enough to partially differentiate, large enough to retain a fraction of its original volatiles, but not large enough to become a real planet, not lucky enough to escape the disruptive influence of the giant next door. The conventional picture was not entirely wrong. Ceres is in the asteroid belt. It did form in the conditions that Jupiter helped make turbulent. It is, in some technical sense, a survivor of a process that prevented planet formation in this part of the solar system. But the framing of that story, the emphasis on failure, on the junkyard, on the inertness of the remnant, missed something important. What it missed is that surviving is interesting, that a protoplanet that formed with the volatile-rich chemistry of the outer solar system then retained enough of that chemistry through billions of years of impact and cold and slow internal freeze. That could still, in the year 2015, show the hydrohalite signature of very recent brine at the surface of an ancient crater. That is not a failed thing. That is a complicated thing, a textured thing, a thing with a history long and strange enough that even the instruments of a spacecraft that spent 3 years studying it could only read part of that history, the surface chapters, leaving the deep interior, the relict brine, the still unresolved chemistry for later instruments that have not yet been built or launched. There is an immensity to the age of it that is easy to say and hard to hold in the mind. Ceres has been orbiting the Sun for approximately 4.5 billion years. In that time it has been struck by countless smaller bodies, each impact reshaping its surface, some impacts large enough to leave craters like Occator, 92 kilometers across. The kind of hole that a projectile of significant size makes when it arrives at significant speed. In that time, the global ocean that models suggest it possessed in its early history gradually froze from the outside in, the outer layers cooling faster than the deep interior, the liquid retreating downward and inward, the ice shell thickening over the course of hundreds of millions of years. The remaining brine growing saltier and denser and colder as the fresher water crystallized out and left the dissolved minerals concentrated in what remained. In that time, the cryovolcanoes erupted and froze and flattened and were mostly absorbed back into the surface, with Ahuna Mons standing as the latest, freshest, youngest survivor of a process that has been repeating throughout the entire history of this world. And in that time, on the floor of Occator crater, the brine seeped upward through fractures in the crust, driven by the pressure of impacts and the slow chemistry of dissolution, and arrived at the surface and froze, leaving its sodium carbonate and its hydrohalite behind in bright deposits that look, from orbit, like 2 torches left burning in an otherwise very dark room. Facula. Little torch. It is a remarkably apt word, borrowed from Latin into the vocabulary of planetary science to describe bright features on otherwise dark surfaces, used here for features that are not literally producing light, but that are so much brighter than everything around them, on a surface that reflects only about 9% of the sunlight that falls on it, darker than asphalt, darker than old coal, that they stand out the way a torch would stand out in a room that had been lit by nothing else for billions of years. The torches are still there. The hydrohalite says they are fresh. The reservoir models say the plumbing is still connected. The mission that found them is silent and orbiting, a monument in a stable path above a world that has not finished surprising us. You found it, in a sense, before we thought there was anything to find. Ceres has been visible to the naked eye from Earth under the right conditions, or at least close to the threshold of naked eye visibility, for as long as there have been eyes on Earth to look for it. Giuseppe Piazzi saw it on the first day of January 1801 through a telescope in Palermo, and wrote down what he found in careful Latin, and the world added a new body to its catalogue of planets, and then took it away, and then added it back a different kind of thing 2 centuries later. And through all of that reclassification and redefinition, the world itself continued doing what it had always been doing: seeping brine, building ice volcanoes, carrying its organics quietly inside its icy shell, slowly freezing its ocean 1 layer at a time, waiting for something with the right instruments to finally look carefully enough to see what was there. Dawn looked, and the answer it found was not the answer anyone was specifically looking for. Because the question, is there still liquid water beneath the surface of the closest ocean world to the sun, was not quite the question being asked when the mission was designed. It became the answer to that question anyway, built from the hydrohalite clock and the deep reservoir model, and the cryovolcanic mountain and the water vapour that Herschel detected before. Dawn arrived, and the organics that no one knew were there until an instrument close enough to see them found them near Ernetet crater in the Northern Hemisphere. This is often how it goes in planetary science. You send an instrument to a place with a set of questions, and the place answers a slightly different set of questions that turn out to be more interesting than the ones you brought. You come back with data that takes years to understand, that changes the category the thing belongs to, that rewrites the sentence that began "the asteroid belt is" into something more qualified, more careful, more honest about the complexity the belt actually contains. The grey lump in the junkyard, the world darker than asphalt, the largest surviving remnant of a failed planet, the closest ocean world to the sun. The relict sea caught mid-freeze. The body where sodium chloride dihydrate was found for the first time beyond Earth, in deposits fresh enough to mean brine is still finding its way upward, still leaving its bright trace on the floor of a crater that had 20 million years to go quiet and declined to do so. Ceres is all of those things. The last few are simply the ones we did not know until recently, and knowing them changes the shape of the story. It changes the shape of the asteroid belt. It changes the quiet assumption that ocean worlds live only in the far cold distances beyond Jupiter, that the inner solar system is the province of dry, rocky, volcanically inert objects with nothing much to hide. Something is hiding here. Something was always hiding here. And now we know what it is, mostly enough to say with reasonable confidence that what sits in the apparent emptiness between Mars and Jupiter, orbiting quietly in a belt of rubble, smaller than the moon, darker than the road outside, is a world that once had an ocean and has not yet entirely let it go. The passages of ice and salt are quiet now. A Hunamont stands in its place, in the grey plain, steep-sided, bright-streaked, unhurried, a mountain built from slush on a world that would have seemed too small and too cold, and too far from the sun to make one. The floor of Occator crater is still and bright with its sodium carbonate, Cerealia Facula holding its shape against the slow processes that will eventually claim it too. The hydrohalite in its surface layers existing for now but not forever, ticking through its dehydration timescale the way a clock counts down in a room no one can currently enter. Dawn orbits above all of it, silent and dark, its instruments no longer transmitting, its trajectory fixed by gravity into a slow, patient ellipse that will carry it around and around Ceres for decades before the mathematics of orbital mechanics finally brings it low enough that the ending becomes something other than an orbit. If you feel moved to share where you are listening from tonight, what corner of this world you are in, what patch of earth is outside your window or above your ceiling right now, I would genuinely like to know. The comments are there, and I do read them. There is something fitting about that, I think. Ceres has been carrying the record of where its water came from, where its organics came from, what neighborhood of the early solar system it was born in, all written in the chemistry of its surface, in the shape of its mountains, in the density of its interior, for 4.5 billion years. We keep our own smaller records of where we are, where we came from, what we brought with us. The places matter. They always have. If this kind of slow journey through somewhere strange and cold and old is what helps you find your way to sleep, there are more stories of this kind here. More places where the solar system turns out to be doing something it was not supposed to be doing. More worlds that kept their secrets until the right spacecraft finally arrived to ask the right questions. They are waiting for whenever you want them. You have done enough for one day. The question Ceres still holds, the depth of its remaining brine, the full extent of its organic chemistry, the quiet progress of Cerealia Facula refreshing itself or not, will still be there in the morning, and the scientists who think about them daily will still be thinking about them. And if we are very fortunate, eventually another instrument will be sent outward past Mars and into the belt, and we will learn something else we did not know. But that is for another time. For now, let the dark be what it is. Let Ceres orbit in its quiet stretch of the solar system, small and grey and bright, with its two little torches, the closest ocean world to the sun, carrying its frozen sea and its record of deeper chemistry through another night that will not look different from any other night to an eye that is not watching closely enough. Close your eyes, put down whatever remains of the day. Good night from up here in orbit. I'll keep watch while you drift.